Hello everyone. Thanks to everyone for watching this video. My name is Qida. I'm an architect and engineer. Today's video is titled Stress and Strain Transformations, and it is going to introduce the Mohr circle of stress and Mohr circle of strain. I am going to give you an overview of what I'm covering in today's video. Firstly at all, it is a bit of background to the topic, and then focus on the stress and strain transformations before wrapping up with conclusions. We are going to take a look at the stress and strain transformation. Let's start by reminding ourselves about the stress element. The stress element is a useful way of describing the stresses acting at a single point within a body. We will consider a two-dimensional stress element, corresponding to a state of plane stress. The normal stresses and shear stresses are shown on the four faces of the element. Let's look at a simple example of a beam under axial load. Our stress element is aligned with the direction of the applied load, and the stress state will be very simple. We will only have a normal stress of sigma x, sigma y, and the shear stresses will be 0. But we might want to rotate our stress element to get the stress state for a specific angle. If there was a weld in our structure, for example, we might want to determine the stresses perpendicular to the weld. Depending how we choose to orient our stress element, we will get different values for the normal and shear stress components. We can calculate what the normal and shear stresses will be, as we rotate our stress element by using the stress transformation equations. Now we will introduce the stress transformation equations. Consider the stresses acting on an inclined plane of the uniformly stressed rectangular block. The inclined plane makes an angle theta with OY and cuts off a triangular block. The length of the hypotenuse is C, and the thickness of the block is taken again as 1 unit of length for convenience. The values of normal stress sigma and shear stress tau on the inclined plane are found by considering equilibrium of the triangular block. The normal stress acts along the normal to the inclined plane. Resolve the forces on the three sides of the block parallel to this normal, and resolve forces in a direction parallel to the inclined plane. Then we obtain the two equations. The expressions for sigma and tau are written more conveniently in the two forms. Square each equation and add, then we have the standard equation of circle. The circle defining all possible states of stress is known as Mohr circle of stress. Mohr circle of stress is shown in the right-hand side. Mohr circle is a graphical method for easily determining normal and shear stresses. The points P and Q correspond to the stress states sigma x, tau xy, and sigma y negative tau xy respectively, and are diametrically opposite. From the Mohr circle of stress, it is clear to see that the principal stresses are defined by tau equals to 0. The maximum shear stress is the radius of the circle. Alternatively, the principal stresses can be calculated more directly without finding the principal planes. The normal stress sigma is a maximum when derivate the sigma equation and equal to 0. Then we obtain tangent 2 times theta. This equation defines the directions of the principal stresses. The principal stresses are also the maximum and minimum normal stresses in the material. The principal stresses are expressed as the two equations. Now we see the Mohr circle of stress. The principal stresses are the points A and B, at which tau equal to 0. The maximum shear stress is given by the point C. The state of stress, sigma tau, on a plane inclined at an angle theta to OY is given by the point R. Now we make an example. At a point of a material, the stresses forming a two-dimensional system are shown in this slide. Sigma x equal to 50 MPa, sigma y equal to 30 MPa, tau xy equal to 20 MPa. Using Mohr circle of stress, determine the magnitudes and the directions of the principal stresses, and also determine the value of the maximum shear stress. From this plot, the shear stresses acting in conjunction with sigma x are counterclockwise, so tau xy is said to be positive on the vertical planes. Similarly, the shear stresses acting in conjunction with tau xy are clockwise, so tau xy is said to be negative on the horizontal planes. On the Mohr circle of stress, construct a circle with the line joining the point sigma x tau xy or 50-20, and the point sigma y negative tau xy or 30 negative 20 as the diameter. The principal stresses and their directions can be obtained from a scaled drawing. Substitute these values into the relevant equations. We can obtain sigma 1, sigma 2 tau maximum and the directions of the principal stresses. We obtain the direction of maximum principal stress is 31.7 degree, and the direction of minimum principal stress is 58.3 degree. Next, we will learn the strain transformation. For two-dimensional system of strains, the normal and shear strains in any direction are known, if the normal and shear strains in two mutually perpendicular directions are given. Consider a rectangular element of material OABC in the xy plane. It is required to find the direct and shear strains in the direction of the diagonal OB. When the normal and shear strains in the directions OX, OY are given, suppose epsilon x is the strain in the direction OX, epsilon y the strain in the direction OY, and gamma xy the shear strain relative to OX to OY. All the strains are considered to be small. If the diagonal OB of the rectangle is taken to be of unit length, the sides OA, OB are of length sin theta, cosine theta, respectively, in which theta is the angle OB mixed with OX. In the strain condition, OA extends a small amount epsilon y times sin theta. OC extends a small amount epsilon x times cosine theta. And due to shear strain, OA rotates through a small value gamma xy. To quantify the movement of B and the rotation of B, we can obtain the two expressions. After simplification, the forms of normal strain and shear strain can be obtained. These forms are similar in the normal stress and the shear stress on an inclined plane. Sigma x and sigma y in the equations are replaced by epsilon x and epsilon y respectively, and the tau xy by half of gamma xy. Square each equation and add. Then we have the standard equation of circle. The circle defining all possible states of strain is known as Mohr circle of strain. Mohr circle of strain is shown in the right-hand side. The points epsilon x half of gamma xy and epsilon y negative half of gamma xy are located. The line joining these points is the diameter of the circle of strain. The values of epsilon and half of gamma in an inclined direction making an angle theta with OX are given by the points on the circle at the ends of a diameter making an angle 2 times theta with PQ. The angle 2 times theta is measured clockwise. An important feature of the strain analysis is that we have not assumed that the strains are elastic. We have taken them to be small. However, with this limitation, Mohr circle of strain is applicable to both elastic and inelastic problems. From conclusions, what we learned? Stress is a physical quantity that expresses the internal forces that neighboring particles of a material exert on each other. Strain is the measure of the deformation of the material. Mohr circle method can be used to transform stresses and strains. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.